Have you ever wondered why I can shoot exactly at this one point, but the probability of hitting any one point is 0?
My bow.
Keep watching. This sentence represents the only valid argument I know why science could be considered a belief. After all, I believe that if I do an experiment today and I do the same experiment tomorrow, I will get the same result. If that were not true, doing experiments would be no use. If the world would be completely different tomorrow compared to today, then how could I learn anything about the world that is useful? But why do I call this a belief? Well, that's simply because I cannot use experiments to refute the whole idea. After all, if a scientist is confronted with an experiment that turns out different tomorrow than today, he will simply blame the conditions under which the experiment was taken. He will simply say, well, you actually did a slightly different experiment and that's why you got a different result. I really believe that this sentence has truth in it. And it has never let me down. I mean, every time something came up different, we have been looking for the reasons why, and we have found reasons why, and that usually has taught us something about the world. So this is, well, it's proven in life that this is a very useful notion. But it is a belief. Well, that is of course a nice party topic for you. But it's also fundamental to the upcoming module on basic statistics, because statisticians, after all, are people who are doing the same experiment over and over again, expecting a different result. Statisticians are realistic. They're not fools. They understand that when you perform an experiment a number of times, you will not be able to completely control it, so you get different outcomes. What they hope is that they control the parameters of the experiment enough to at least be able to describe the outcomes using probabilities. And even such a probabilistic model is going to be an approximation. If I throw a dice a lot of times, then at the beginning my hands are dry, but as stakes go up my hands may be sweaty, which may actually influence the way the dice are rolling and thrown and may influence the probabilistic outcome. But the idea that we can capture the outcome of an experiment using a probabilistic model is not a belief. It is a scientific hypothesis. Like we've seen in the lecture on the scientific method, you can actually refute a probabilistic model by doing experiments. In this module, I'm going to show you how to do that. But before we get to that, it may be a good idea to be a little bit more precise about what we mean by probability. The rough idea behind defining probability is that we're going to perform the same experiment a number of times and then count how often we observe a certain outcome. So mathematically, you might model that as a set omega containing all the possible outcomes of the experiment and a function from omega to a value between 0 and 1 that represents the average number of times a certain outcome shows up after performing the experiment. So if we perform the experiment a large number of times, say n, and we count k instances of an outcome, then the probability of that outcome would be k divided by n, approximately. But this model is not very useful if we want to consider sets of outcomes that are more complex. For example, let's say that there is a ballistics expert in the room, my mother. She would never just let me throw the dice when we were playing a game. She would always be concerned about the precise trajectory that the dice would take through the room, even though the outcome is the only thing that actually counts for the game. No, she would be concerned that the dice would not end up within half a centimeter of these crystal figurines that we have in the closet. So How can we take that into account? How can we take into account the idea that the outcome of a dice roll is actually not 1, 2, 3, 4, 5, 6, but is the precise trajectory that the dice make through the room? Well, of course, we could start by taking omega to be the set of all possible trajectories. But then we run into a problem, because this set is infinite, it's uncountable in fact. And that means that it does not make sense to count different outcomes to determine the average. In an uncountable set, you will never be able to see all the possible outcomes. Every outcome most likely will only occur once, so taking averages really is useless. And there is another problem, namely that if we want to determine whether a certain outcome occurred after doing an experiment, we could of course measure what the precise trajectory through the room was. But that measurement would always be an approximation. We would never be precisely characterizing the trajectory. Now, luckily, these two problems can be solved at once using a mathematical concept called measure theory. Consider that we want to know the distance at which the die landed from the crystal figurine. We can take a piece of measuring tape and easily see if the distance is larger than a centimeter or closer than a centimeter whenever the die sticks out in one direction or the other of the centimeter marking on the tape. But if it really gets close to being at 1 centimeter, we may need to zoom in and perform a second measurement using a more precise measuring tape in millimeters. Again, if it really gets close, then we might even need a more precise measuring tape and we might need to zoom in even more. Every measurement we take divides the set omega of all outcomes into a set that fall within the measurement, the set M, and a set that fall outside the measurement, the complement of that set M. And that's how mathematically we will look at measurements, at a set M and its complement dividing the set of outcomes. So for a mathematician, it doesn't matter whether the measurement was performed using a measurement tape, using a ruler, using a laser beam, as long as it gives the same outcome, the same set of outcomes, it's the same measurement. It's probably clear now that even if one measured set M contains uncountably many possible outcomes, we can still count how many outcomes of experiments fall in either M or the complement of M. That is just a finite count we can make. So we can perform n experiments and count that k outcomes fall into M and then n minus k fall into the complement of M, and we can assign probabilities saying, oh, the probability of M is approximately k divided by n, and the probability of the complement is approximately 1 minus k divided by n. And that's the first law of probabilities, that the probability of a complement of a set is 1 minus the probability of the original set. Next, if we perform two measurements, M1 and M2, it is clear that we can consider M1 intersected with M2 as a kind of combined experiment, which we only count if the outcome falls both in M1 and in M2. And the same, the union of M1 and M2 can also be considered as the outcome of a combined experiment, which you can determine the count for using a finite amount of effort. Also, for the complement of these sets, you can determine with a finite amount of effort whether the outcome of an experiment falls into that complement. Now, there is a special case in which M1 and M2 are non-overlapping sets. In that case, if I find K1 outcomes in M1 and K2 outcomes in M2, and M1 and M2 do not overlap, so their intersection is empty, then the number of outcomes in the union will be K1 plus K2. Of course, if M1 and M2 do overlap, there is a chance that I have been counting certain outcomes twice, but if they do not overlap, it's exactly this sum. That gives us the second law of probabilities. If two sets are disjoint, then the probability of the union is the sum of the probabilities of the two sets. And we can go even a little bit further. If we have an uncountable sequence of measurements, 1, 2, 3, 4, 5, 6, etc., then we can determine with a finite amount of effort whether the outcome of an experiment falls into the union of this sequence. Because we can just check every element of this sequence one by one, and if it falls into the union, then it will fall into one of these at some point, and as soon as we've detected that, we know that the outcome of the measurement falls into the union. So we can say that even a countable union of measurements can be considered as a finite measurement. The problem is that for the complement, this is not true. We cannot define or determine with a finite amount of effort whether the outcome of an experiment is not in this union. Still, if we are talking about probabilities, we can define the probability of a countable union as the sum of the probabilities of all the elements in that union, provided that all these elements are disjoint. And we can use the law for the complement to determine the probability of the complements. So mathematically, we can consider countable unions as measurable sets and complements as measurable sets. In any advanced text on probability theory, you will therefore find the definition of sigma algebra as being a set F of subsets of omega, such that whenever a set M is in F, because F was a set of subsets, whenever a set M is in F, then also the complement is in F. And when you have a countable family or sequence of sets in F, then the union of this sequence is also an F. And these two combined, of course, mean that also the complement of that union will be an F. The elements of the sigma algebra are called measurable sets, but if you compare this with the idea of what we think is measurable, then you'll find that sometimes also these limits are considered measurable, even though there is not a finite way to measure them. But we have a way to define a probability to them that seems reasonable. In practice, the sigma algebra is usually made by first considering which sets are really finitely measurable, and then taking the closure under complement and under countable union. And if you then start determining probabilities, you do the same. You just determine the probabilities for the finitely measurable sets, and then the probabilities for the complements and the unions actually automatically follow from this. They are derived from this in a way that is consistent with the already existing sets. Given a sigma algebra F, a probability measure is simply a function from the sets in that sigma algebra to a value between 0 and 1. And it should satisfy the axioms that we already discussed, namely that a countable union of sets has a probability that is equal to the sum of the probability of each of these sets, provided that the elements of this countable union are disjoint. And the probability of a complement set is 1 minus the probability of the original set. The tuple omega f and the probability function together is called a probability space. Now, I promised to explain to you how it is possible that you can shoot exactly at a certain point and still find that the probability of shooting at exactly that point is 0. Of course, that is a result of the way in which we just defined probabilities. If we look at any probability space, then it could be that we have two outcomes that really cannot be distinguished from one another using measurements. If that happens, then this precise outcome is actually an unmeasurable set in itself. That singleton is an unmeasurable set because it cannot be distinguished at all from the sets around it. If it's an unmeasurable set, then talking about the probability does not make sense at all. If it is a measurable set, it can still be a measurable set, then, as is the case for this arrow, it could be that you can distinguish it from the points around it, but to distinguish it from all the points around it, you would need an infinite number of measurements. Every measurement distinguishes it from some points, but if you need to distinguish it from all points, you would need an infinite, or actually an uncountable number of measurements. When that happens, the limit that you take to determine the probability of that one point is very likely to go to zero. Actually, in a practical situation, it will always go to zero if you need an infinite number of measurements to determine an exact spot. That is different from a dice roll where you throw a 1, a 2, a 3 or 4, which is also an exact outcome in some definitions of omega, but that exact outcome also has a single measurement that goes with it. I hope that this story makes clear to you why we always talk about probability of sets rather than of single points. And I hope this story encourages you to, whenever you're reporting on probability, think beforehand about what your set of outcomes is and what you consider measurable in the situation that you're in. And of course, whenever you find a set that has probability 0, I hope that you will realize that that does not mean that the things that are in that set cannot happen. Maybe they cannot happen, maybe that is why the probability is 0, but it could also be that you're simply in the limit of what is measurable. And what it means if the probability of a set is 1, I think you can figure that out for yourself.